don't know, Tachyon is part of the scaling mandate that the Zcash engineers are currently working on. It addresses a specific problem by introducing a bunch of new novel cryptography and techniques around information retrieval, information pruning, private querying, and things like that. We'll get into all this. Looks like in the chat we have a Tachyon emoji now, so congratulations on that, Sean. You've reached Discord emoji level of fame with your work. Yeah, I think this will be an exciting thing. I think people definitely have a lot of questions about this project, and this will be a good opportunity to use the platform to talk about it. So, Sean, why don't you go ahead and introduce yourself, and then we'll dig into Tachyon.
Sure. So I'm Sean Bowe. I'm a core protocol engineer working on Zcash. I've been here since the beginning, since year before the project launched. And I've been involved in all of the different shielded pools that we've and network upgrades that we've done over the past many years, as well as the initial launch. And so my main focus has been, at least at first in Zcash, it was with just engineering and a little bit of cryptography. And as time went on, I got more involved into the cryptography, and kind of a common thread was that I was trying to solve all these more or less scaling problems with Zcash. So we had slow snarks, and we had trusted setups that couldn't really go beyond a handful of people, and things like that. So I focused on that, and I was able to make some discoveries, and with the help of the other engineers and cryptographers at the Electric Coin Company at the time, we were able to ship those in each of those network upgrades I was talking about. So Sapling kind of made snarks faster in Zcash, so made it so you can actually send shielded transactions on your phone. And then later on, Orchard, the most recent update, the one that pretty much the shielded pool that everybody uses now, is using Halo, or Halo 2, and that doesn't require a trusted setup anymore. So it was mostly a feat of engineering than anything. In the kind of interstitial time, Halo was a academic paper that I worked on with Dara Emma Hopwood, and Jack Grigg, and we described a new way to do recursive proofs, which ended up starting this whole a new field of cryptography. I'm going to talk about recursive proofs in a minute, because they actually come up a pretty central topic in Tachyon. And so lots of papers emerged that improved on that concept over the last several years. So that's pretty exciting, but we actually have never actually deployed the actual tricky part of Halo into Zcash yet. We deployed Halo 2, which is like this. I can go into the details, but the central part of Halo was not actually integrated into Orchard. It set the stage for it. It was like a transition upgrade, or more or less, to the cryptography we were going to use. And so, yep, that's pretty much what I've been doing over the last year. Has been working on this new upgrade called Tachyon. Technically, I've only started ramping up last fall, so in October, November, made my first hires, and I've been getting a team together to work and develop and implement this ambitious upgrade. And the idea behind it is to actually deploy Halo, the real cryptographic technique inside of Halo, to deploy these things called recursive proofs in Zcash, and to use them to solve scaling problems that exist inside of the cryptography, inside the shielded transaction cryptography that we use in Zcash. And there's some clever tricks and kind of novel ideas that came about during that process of developing that, starting at last ZCon, where I kind of describe this general idea of trying to come up with hacks to get around some of the scaling challenges using recursive proofs. And then later on, throughout the design of Tachyon, we've come up with simplifications that actually really improved the architecture of the shielded pool. And I think future shielded pools in Zcash, whether they're Tachyon or not, are likely going to be built this way. So we'll go into the more of the details of the actual cryptography and the actual scaling challenges that are solved. But on a bird's eye view, that's essentially what Tachyon is, what I'm working on. Is just a way to fix these bottlenecks that exist inside of Zcash's shielded transactions today. And people talk about scaling in cryptocurrencies. They could be talking about like a million different things. For example, the consensus protocol may need to scale just in pure terms of bandwidth. Or finality, or all these other different things come into the scale question. The focus of my project with Tachyon is to fix these core issues in the actual private payment part. That's at the core, because if those bottlenecks are significantly worse than Bitcoin, which they are, then all this talk about improving the consensus protocol is great and should happen in parallel, and I'm all for it. However, we need to scale the central part, the thing that actually sets Zcash apart, the private payments. We need to scale that to make all the other scaling challenges even worth trying to solve. So yeah, that's my sort of vague, high-level explanation of the project.
Cool, and just
people are saying I can't hear anything in chat.
Yeah, I know. I asked for a show of hands in the chat. It's 7-2. Oh, can you hear me, Sean?
Hello?
Oh, no.
Uh-oh.
Everybody restart Discord.
I've been talking myself for 3 minutes?
No, can you hear me, Sean?
Mark, I can't hear you if you're talking.
Shit. I'm going to restart Discord. I'll be back.
Weird. I cannot hear Mark.
Okay.
Huh. What the heck? No! Okay, now I can hear you, Mark. Could you hear me the whole time I was talking?
I did.
Okay, weird.
And others can hear you. About 80% of people can hear, but 20% still cannot. Zero Dart suggests turning off VPN. I restarted Discord and that worked fine. People can hear you. I don't know. I think we should just continue.
Okay. I didn't click anything as far as I know, like my UI, so I don't think that I think it's working.
I don't think Discord is very good, unfortunately. But
I'm using the Discord web app, so I'm not sure if that causes problems. But
no, it should be fine. It's worked.
Where's the deafen button? I don't see that. Is that a joke?
I think that was a joke.
Okay, all right.
Yeah. Oh no, it's real. Holy shit! There's a deafen button. Look at that. Yeah, so if you click on the microphone and the arrow menu next to the microphone, there is a checkbox called deafen, which I really don't know what it does, but maybe it mutes somebody and lets them talk and think that, like the bozo feature on old forums. Do you remember that?
Yeah, I know what you're talking about. That's funny. Yeah, that's great.
Yeah,
that's hilarious.
Okay, we're going to discontinue. I'm sorry about the technical difficulties, but it is not us. It is Discord. We're going to have to just keep on keeping on. Yogi, do we at least have audio in the recording? I guess that's the most important thing. Let me know. Sean, you're self-taught, are you not?
Yeah, I am
I think that's
self-taught. Well,
important.
I mean, to an
Yeah,
extent, I'm not really sure what self-taught means anymore, but like I didn't go to school. That's all that means to me.
yeah, that is what I mean. I mean, in the classical sense, I think a lot has changed in the 10 years that you've been working on this stuff in terms of like what self-taught means. But I think in the classical sense, it's important to call out because I think people think cryptography is, well, it is a very esoteric practice, but it's not like magic, right? Like you can kind of learn about it if you're motivated. If you're intrinsically motivated, like you were, I think it's important that people like strip away some of the intimidation there. It's still like a remarkably challenging endeavor, right? But
Right.
I think it's cool that you're self-taught.
Yeah, no, it's I I like to tell people, like insist to people, and I'm not just trying to be smart or something, but I like to insist to people that the cryptography we work with is actually not that complicated if you have the time, and not that much time to learn about it. It really isn't that bad. Um, yeah, I would say it's not too bad. However, every time I tell somebody that,
You're like, oh,
then
whatever. Yeah.
I try to explain it. Um, yeah, it doesn't work out well. Just ask my wife. That's funny.
Yeah, yeah. So given that, and then on the other side of that, I think you're being slightly modest because the key innovations between sprout and sapling, and then sapling to orchard, and now orchard to tachyon are pretty remarkable achievements. So kudos to you and the team and everybody else that worked on it, Diorama, Hopwood, and Strad et al. Um, can you just, before we dive into Tachyon, can you talk about how the primary intuitions from Orchard led to the recursive proofs of Tachyon? I think that's a cool
So
progression.
the question of using recursive proofs in Zcash to solve scaling problems goes back to like the beginning of Zcash. Uh, we were talking about using recursive proofs before we even launched. So, and it was to solve, or at least try to solve, the exact problem that Tachyon's trying to solve. Um, so, in order to prove that you haven't spent your private coins before without identifying which coins you've spent, turns out that's a lot trickier of a problem than merely proving that you had at some point coins to spend. The latter is a lot simpler to do cryptographically, but the former is a lot more complicated. And the way that we do it in zero cash like protocols, and not just Zcash, but like Monero does the same thing, is you release this sort of revocation token to the public as part of your transaction, and you prove that you derived it properly using the snarks. And it's called a nullifier. And this nullifier is kept in a list by all the nodes in the network, and they refuse to accept new transactions that repeat the nullifier a second time. And that's how you achieve double spend prevention. So you get the spending part just by proving you have had some money at some point in the past, like pointing to a Bitcoin block and saying, "Here's a transaction. Here's an output in that transaction. I can spend it." But then using zero knowledge proofs to hide the fact that you're doing it. Well, how do you prove that you haven't spent it before? It's with this nullifier thing. We had thought back in the original, before we launched, we had thought, okay, well, recursive proofs are becoming practical. In fact, the authors of the most practical recursive proofs that were being built at the time were our main scientists at the Electric Coin Company, basically, or whatever it was called before. So we thought, okay, how do we solve it? Well, what the user could do is they could prove they haven't spent their money, just like they could prove that they had money before. You could potentially prove that you haven't spent that money before. So you prove essentially that this nullifier isn't in a list. You can use a different kind of accumulator called a set non-inclusion accumulator than the one that we use to prove that we have money. And we know theoretically it's possible to do this. It's just really slow. And that list grows linearly with the number of transactions that have ever taken place. It doesn't get pruned. So we thought about it and then decided that was way too ambitious, and the snarks that we already had were slow, so we weren't going to do it, but it was just something on our mind. Then as the years went by, we thought about scaling, and Dara actually has this great scaling presentation that Z did in Amsterdam or wherever, some ZK summit or something like that, ZK proof workshop or something. And it's a scaling focused talk that just goes into the cryptography of Zcash and our shielded pools. It says, here are the things that are like asymptotically costly in Zcash, and here are the ways we can solve it. And it's actually very thorough. And it kind of laid out a roadmap for how we were going to fix the Zerocash protocol to make it scale. And one of the main things that you would get at the end of this talk is that solving the biggest problem in Zerocash for this nullifier thing, the scaling this nullifier thing, that was still, I mean, there are ways to do it that Dara had talked about. They were kind of speculative, but we hadn't really actually figured it out yet. And so that's how things sat for many years. In parallel, we knew that we were going to need recursive proofs to do it. So I was working on basically for about 8 months or so, back in 2019 or so, 2020 or so, whatever. I was working solely on recursive proof research while I was at ECC. And that's what turned into Halo, and actually Halo, kind of made recursive proofs practical while also making it so they didn't require a trusted setup. I think I'm going to have to take a break to talk about what recursive proofs are here in a moment, but for a moment, so when we actually started thinking about, okay, now that we have recursive proofs, what are we going to do? One thread of that turned into, okay, well, we need to get the cryptography from Halo actually into the protocol, and that's what turned into Orchard in Halo 2. But then the second thread was, how do we actually use the recursive proofs to solve the scaling challenges? And the idea is that we had to do that. If you go back to Dara's talk in Amsterdam, the ideas we had to do that were really like half-baked, speculative, like I was saying, and they seem messy. And we hadn't made much progress since then. So I kind of took a back seat for our other changes. So fast forward several years, and I left the Electric Coin Company in 2024, and at the end of 2024, and I focused entirely on working solo, individually on Zcash scaling work as a community member rather than an employee for ECC. And during that time, I was thinking about exactly this problem: how do we use the recursive proofs to do this? And came up with some tricks, and then eventually teamed up with Ian Myers, who's one of the Zerocash authors, and we figured out how to create a more systematic way to analyze how to solve the problem. We ended up posting an academic paper about that, which I'll talk about in a second as well. And that's essentially where the recursive proofs fall into the story. But I guess now, as I'm rambling, I guess I could go back and explain what recursive proofs are. But another segue, I can. Yeah.
Yeah. Can you hear me?
Yeah, I can hear you.
Okay, good. Yeah. No, that's a perfect spot. And just to recap, the nullifier problem is this linear growing set of. You can think of nullifiers in two. I think of nullifiers in two ways. One is that they're sort of like receipt IDs for every transaction that happened, and they're all unique, and you need to produce a valid one, and then they get stored in a pile. And you can the other way you can think about them is that they're all turds, and you just have this giant pile of turds that grows linearly all day, every day, forever, and it will never go away. So, given that problem, what are recursive proofs, and how do they solve it?
All right, so it's tricky. I've never really actually sat down to explain recursive proofs like to a general audience. I will say that if you know what snarks are, you're at least halfway to understanding what recursive proofs are. So snarks let us take a computation and prove that we ran it locally on our own computers or our phones, and that the computation like produced a certain output or said yes or no or whatever it did. And we get this tiny proof, and we can put that in our transactions and post it publicly. And that computation can be anything we want. So as Zcash protocol developers, we pick a special computation that encodes all the rules of the private transactions in them. And you basically simulate running the transaction locally, more or less, in this computation. And in this world where you're running this computation is actually very slow. The goal of it isn't actually to do it quickly. It's just to prove that we did it so that we don't reveal the inputs to the computation, which are our private wallet information, like how much money we have, when we received it, our history, and all that stuff. So it's totally okay to do it really slow if we get this proof at the end. And that's essentially what a snark does, or a ZK snark. And so snarks are great. You can do pretty much anything with them, but usually the proof that the computation you're proving is like set in stone, or is either super general or is like very rigid. And usually, and so snarks are useful. But what if your computation is a long-running computation? What if it is a computation performed by many people over time, not just in one step? So snarks are a very one-shot thing. You produce the proof and you're done, and the private inputs are gone at that point. You might, the user doesn't need to keep them around anymore. You've created the proof; it's over. But with this other things, with recursive proofs, we're trying to think, okay, well, what if I want to give you a proof, and you want to build on it, and you want to say, okay, I'm going to give a new proof that my computation, what it does is it actually checks the recursive proofs that I gave you and verifies it the same way anyone would with access to the proof, and then adds a little extra detail, like checks its separate computation, separate predicate of some sort, same time, producing a new proof. Again, these proofs they're succinct, so they actually they're the same size no matter. You can make proofs of different computations that are going to be generally the same size. And so theoretically, if you could do this, which is what we call proof composition, you could I could give you a proof, you could build on it, and give me a proof back, and I could build on that or give it publish it publicly. Perhaps people could take two proofs that somebody else, two completely different people produced, and combine them together and then perform some other state transition. So if you think about it in terms of a state machine, where the proofs essentially authenticate the current state as having been produced by some valid set of computations according to some prescribed rules, then that's essentially where you get this concept that we call proof carrying data, which is this general idea of using using proof composition to do this. And we call it recursive proof composition. The proofs, they don't just compile once. You're not just checking once. These proofs check other instances of themselves. And they can do this basically forever. Cryptographically, it gets more complicated than that, but for the most part, they can you can check this forever. So I could have a computation that goes on for years that we're all building on top of and improving, and you don't need to maintain all the proofs that happened in the meantime. You don't need to maintain the ones from like a year ago or 2 years ago or whatever. You just need the latest one, because the latest one certifies the current state of the machine at that particular step, and that's all you need in order to build on top of it. This other concept called incrementally verifiable computation is related to proof carrying data, but anyway, if you're curious about the literature about that, you can look that up as well. So
Yeah, how to stay on top of this stuff a little later. That's a question I definitely have. But main intuition there, though, is that the size of the proofs are constant, right? They do not grow in size, or do they?
Yeah, they don't grow in size. That's right.
Okay, so if it's n number of bytes, I can take your proof, kind of append mine on, and then it all kind of compresses down.
You can take multiple proofs, put them together, and compress is a word I like to use, but also is sort of somewhat misleading because it's not necessarily compression, but it is fine for now. I guess it makes sense. Yes, you can take multiple proofs and more quote unquote compress them into one proof, as long as the final proof is like, as long as the state that it's certifying doesn't grow in size, right? If I have a proof that says some data, and then you have a proof that has some data, and we combine them, it's not like you get one proof and you get the concatenation of the two pieces of data. It doesn't work like that. You have to like combine them computationally somehow. So you don't get like free. This isn't a perpetual motion machine or anything. You do have to graft this technique onto an actual computational architecture, or like a onto a long running computation in order for it to make sense.
Yeah. Okay. And then the proof itself, that those bytes are the things that are put on chain. Yep. Is that right?
I can't hear you again. I wonder if you have to rejoin.
Shit. Okay, I will rejoin. Keep talking.
I'm gonna look in chat while you. I cannot hear you at all. So yeah, okay. I'm gonna look in chat and see. Let's see. I'm running the show now. The minification of all the recursive proof chains. Yes, that's cool. I guess I can talk about that a little bit too. Mina is like the perfect example. If somebody sits down and goes, "What can I do with recursive proofs?" If you're like trying to write an academic paper saying, "But I've made recursive proofs a little bit faster" or something, in your introduction paragraph, it's going to be something about succinct blockchains, which is what. I gotta invite. I cannot invite Mark to speak. I don't know how to do that. Maybe I don't know. Okay, there we go.
Somebody else invited.
Okay, cool. Sorry, I started talking about Mina a little bit. So Mina's a blockchain that uses recursive proofs to make it so that the computation that you're grafting onto the proof, the recursive proof architecture or concept, is a blockchain validity proof. So I don't give you the whole list of blockchain, the whole list of all the previous blocks. I don't give you all the transactions that took place before. I just give you the current state, or some actual, to be more specific, some commitment to it, some accumulator of the state, and a proof that says that according to the rules that have evolved over time, it produced that state. And so that's one example of using recursive proofs. We don't use recursive proofs to solve the blockchain validity stuff in Tachyon. That isn't our focus. But yeah.
Right. So the proofs that are generated by Tachyon, which I will use your terminology, computationally graft the nullifier spend onto the proof. I'm just trying to make sure I say the right nomenclature and like terminology here, but what you're doing is asking, was this nullifier spent? Was this nullifier spent? Was this nullifier spent? Over and over and over again. And each one of those answers to that question generates a new proof, and that's what's stored on chain.
Yeah. More or less. There's different ways to do it. Obviously, as the chain evolves, proving that you haven't spent your money becomes an ongoing process. Different than proving that you have money, because if I had money, ignoring double spending, if I had money at one point, then all I have to do is prove that my proof or my witness for that money existing previously is an ancestor state of the current state, which is very trivial. It's not like your money it's unexisted at some point. That's not exactly how it works. Now, you might spend it, and in which case you reveal the nullifier I'm talking about. And so it becomes an ongoing process to prove, yes, in this block I also didn't spend the money. Okay, there's a new block. Okay, I didn't spend the money in that one either. So that when you do go and spend the money, you can demonstrate to everyone that you didn't spend it in the most recent blocks. So that's the tension that makes it a little bit trickier.
Okay, cool. And this is an intentionally kind of fun question here. So that all sounds great. We just replace the linearly growing nullifier storage with this proof, and we're done, right? It's just like Orchard with this thing, and right?
Yeah, that's the tricky part. Is that the proof is really, really expensive to make. And like the user's not going to be on to make it all the time. So if everybody's making transactions on the chain, you don't want someone's phone to go through and say, I didn't spend in this block, I didn't spend in that block. You want to give somebody else the ability to make that proof for you, generally. And that's where the real challenge gets to be, because we know how to scale that part, but we don't know how to make it private. Well, we do now with Tachyon. However, before we just assumed that we'd have to compromise somewhere, and you'd either have to like tell some server, hey, I have some money, here's some info that will let you kind of figure out what I got, maybe not all the details, but at least some of it, and you can maybe distinguish my transactions on chain or whatever. I need you to make this proof for me so that when I turn my phone on and open Zottle or whatever, it shows me I can spend my money and I could just make a transaction by connecting to your server and grabbing this proof that was for the latest version of the blockchain. And doing that privately is tricky. So that's essentially the idea behind Tachyon, is solving that problem specifically. So there's nothing revolutionary about the idea of proving that a nullifier hasn't taken place. There's nothing necessarily revolutionary about proving non-inclusion in a set. And using recursive proofs to do it helps a lot. And the reason why recursive proofs are helpful for this, by the way, is specifically because the blockchain evolves over time, and so if you prove non-inclusion up to a certain point, you just have to update that proof again to say, okay, in the latest block, I also didn't spend my money. So that's why recursive proofs are useful. They naturally handle that sort of a computation. Just wanted to throw that out there.
Is there a post-Tachyon protocol analogous to Sprout versus Orchard that somehow makes them mobile friendly, like Orchard did?
Well, the idea would be... I see what you mean. Well, the whole idea behind Tachyon is that if these servers are doing this and it's made private, which is what I can talk about in a second, how we do that, then the user's phone actually does a very insignificant, like Orchard, of the same order of magnitude as Orchard, amount of cryptography locally on the phone in order to spend your money. And so it should actually be nice and quick. Halo kind of itself, which is the recursive proofs we're actually using in Tachyon, it sort of solved the problem of making the recursive proofs efficient in our version of the cryptography, or in our kind of world of the cryptography or elliptic curve based stuff years ago. And so that problem is sort of solved, but you still have the problem, even if it's really cheap to make these recursive proofs locally, you're talking about consuming information from the blockchain, these nullifiers that everyone else is revealing, and proving non-inclusion within those. And that's something that you can't do offline, and you certainly cannot do it quickly, just as you turn your Zcash wallet on, and what are you going to download the whole, like all the blocks that happened since the last time and computed proof locally? It's never going to happen. I don't care how fast the recursive proofs get. It's just not feasible. It doesn't scale that way either. You need these remote servers to be able to make progress without learning anything about your wallet.
Okay, cool. So we need these remote servers. Sean, how does this not become a centralized disaster that reveals everybody's private information?
Right. The solution is to actually change the way the nullifiers work. So, if we're willing to sacrifice certain properties of the nullifiers, it turns out that we don't care about that much in practice, or at least that we can mitigate those. Those properties of the nullifiers exist to solve certain security issues that we can solve other ways. Doesn't matter. If we're willing to put that aside, we can actually redesign the nullifiers to work slightly differently than the way they work in Zerocash and the way they work in Sprout and Sapling and Orchard. In those protocols, when you reveal your nullifier, it's done. Like you've revealed it, everyone remembers it, and there's just one nullifier for every one of your so-called notes that you're spending. In Tachyon, it changes because now which nullifier you reveal depends on when you spend your money now. And so that changes things a little bit because now the double spend prevention needs to prove that in these different epochs throughout the history of the chain, at least up until when your note was created, that your nullifier for each of these epochs was not revealed in that epoch, the blockchain. Or something related to that overlapping with that captures the predicate that I'm describing. If you're able to do that, then you've done effectively the same thing as the nullifiers that are used traditionally in Zcash. You've achieved it already. So that's essentially the trick, is to just make the nullifiers epoch based. And so by doing that, you reveal a nullifier. You reveal the most recent one, or maybe the most recent two nullifiers for your note whenever you spend it. And the proof that you attach to your transaction proves non-inclusion of the nullifiers that took place before that. And all of the nullifiers are derived from a shared key derivation function or whatever, but they are unlinkable with each other. So, or PRF or whatever, they are unlinkable with each other. So you could potentially give a remote server these nullifiers and say, okay, I need you to prove non-inclusion for these blocks for this nullifier, and the service can give you back that proof, and they could remember your nullifier that you gave them and everything. You could send this in clear text. You could have a totally compromised channel with a third party, and that nullifier is not what you reveal on chain. You reveal the most recent one. That isn't the one that you tell the service. So the service is basically proving you didn't cheat and double spend before up to a certain point. But then you do have to reveal a nullifier eventually. It's just it's not the one that you give the service. It's essentially the trick. So the service has to somehow prove that the nullifiers are related to each other without learning your actual secret or how to derive like the future ones. That's a simple task of just clever key derivation design, but that's pretty straightforward. So once you do that, then the service can be given the capability to create these proofs for you without learning anything about the transaction that you actually reveal on chain. So the service is not trusted whatsoever. They are performing expensive computation, of course, but they don't get anything about your private information. They do not, or about your wallet. They do not have a capability to distinguish the transaction that you eventually publish on chain from any other transaction that they see. So they don't know which ones they contributed to, or likely or not will be the ones that you used. Or that they assisted you in being able to spend. They won't be able to see that. All the transactions sort of look the same still. You still get this indistinguishability or ledger indistinguishability property on chain.
Okay, some questions about these services. One thing that trips me up when I think about this is if we get our way and Zcash is scaling to billions, there's going to be like transactions and nullifiers and keys flying around here. Are they necessarily ordered, or can multiple servers kind of just generate proofs and they're all going to be valid somehow? That you see what I'm asking?
Sorry, you mean by ordering? You mean like different epochs? Is that what you mean? Sorry.
Yeah, I guess just how do I know that the proof that I'm generating contains all the necessary nullifiers to validate your proof, and then when I get the next one, a bunch of other proofs will have happened in parallel to me.
So
Like,
definitely, the recursive proofs allow for this sort of parallelism to take
yeah,
place, where
yeah,
you can have some services that are proving non-inclusion for one nullifier, while others are proving non-inclusion for the other, and you can stitch them together. You can either have the services do that for you, or you can do it locally. It doesn't matter, because either way, the services aren't going to learn about your the linkage between the nullifiers or even the proofs necessarily. And
have this sort of an eventual consistency baked in that after all is said and done, all the messages are passed. Theoretically, all the nullifiers will have been sufficiently proven.
right, and that's the proof that you generate, that you publish. You publish the proof in your transaction that convinces everyone else of that. So whatever the stitching process is for taking these little computational steps and merging them together or whatever, those are all part of the rules of how to make that final proof, more or less. So yeah, if that final proof checks, then yeah, you didn't cheat. You have all of you didn't spend your money previously. Clearly, because the proof verifies. So these services are just helping create the parts of the proof, and you're stitching them together, or they're stitching them together for you too. But there's a limit to what they have to learn about the actual computation they're doing. Like they're definitely going to learn, at least in our protocol currently, they're going to learn the nullifiers you ask them to prove non-inclusion of. They are going to learn the old proof state, but that doesn't reveal much because they're just random proofs. Really, they're completely like arbitrary looking. But they don't have to learn anything about your note. Like they don't have to learn how much money you have in the note or when it was created or anything like that. They don't even have to know necessarily that the note exists. It can be a fake note, a dummy note that you make. You're just like asking the service to waste computation, making a non-inclusion proof for a nullifier that doesn't actually represent a spend attempt on chain. So they don't necessarily have to learn anything about your wallet, because we can hide the state information within hiding commitment schemes inside of the cryptography effectively, so that the local wallet, your wallet on your phone, knows how to prove that the nullifier non-inclusion proofs that were stitched together all relate to the same note, but it's not necessarily enough information for the service to learn anything about the correlation between different notes or anything like that. It's very flexible. This whole thing is extremely flexible in terms of what information you give out, and if you just design it well, almost all the time you can make it so that the remote services doing these recursive proofs for you don't learn anything sensitive about your wallet.
Awesome, thank you. Now, as I understand, due to all of this, there's sort of this exercise of like, well, now that we have this technology, what data actually need to be on chain versus what data doesn't need to be on chain, and how does Tachyon change this? I think people have a ton of questions about this. And yeah, what changes in terms of what's actually stored in the chain? Is there even still a chain? Like what is the data availability story look like, and what is the on and off band story look like here?
Yeah, so Tachyon's focused on solving this nullifier problem, but there are other things it solves with the recursive proofs at the same time. I'll get into that in a second. But solving this nullifier problem means that while your nullifiers are revealed on chain, the fold node validators can prune them. They can discard them over time, just same way that in Bitcoin you can prune old spent outputs from like 1,000 blocks ago, because you don't expect there to be a rollback. Full node can do the same thing with nullifiers in Tachyon, which means that there's nothing anymore inside of the actual shielded transaction protocol that requires full nodes to remember anything anymore. Anything that grows linearly anyway. So they remember the current state, obviously. That matters. We got to check against it to make sure your proofs are valid. But that state doesn't grow. So there's no state growth problem ever for full node validators. The chain may grow, but that solves that problem. That's nice because logically we go, okay, well, if the core shielded protocol doesn't need to store anything on chain that everyone needs to remember anymore, then what are some other things on chain that we can get rid of? Which is a separate question entirely, and it's just a matter of almost a philosophical discussion about scaling and UX and things like that come into play, which is essentially what you're getting at. Do we need to put all this other stuff that we put on chain? The thing to note about the way that Zcash works today is that the proofs are big, and so when we originally developed Zcash, we actually put a bunch of crap in the transactions, like these memos and all the rest of this stuff, and we thought, oh, who cares? I mean, we might as well do it because the proofs are big, and you're putting those in the blocks. You might as well put a little memo in there, you might as well do this, you might as well do that. And so so once we talk about using these recursive proofs, first to solve this pruning issue with the nullifiers, and then, which I'll go into detail in a moment, this aggregation concept of actually making it so these proofs go away, or at least they amortize away within a block, you're actually left with a very, very small amount of data. In fact, over time, as you see the architecture, there's only like a few hundred bytes left of your shielded transaction, and none of it needs to be permanently remembered. If you know Zcash, you know that you're allowed to send a 512 byte memo currently in Zcash. And so the memos are now bigger than the actual marginal transaction size inside of Tachyon now, or at least very almost identical. It depends on what you're doing and how many notes you have to spend and stuff, but more or less it's very comparable. Which kind of, if you're talking about scale, you might want to say, okay, well, let's pare down the size of those memos to just either the bare minimum. My personal philosophy is that the memos don't deserve to be on chain at all, and we should use separate mechanisms somehow to communicate them between the counterparties. But there's trade-offs with that because the memos are in a very convenient spot on chain. There's like a shared expectation in the community that the ledger history is archived and accessible. The memos are sort of transactional with they cling on to the actual transaction, so they're authenticated in a sense. They're used as backup and restore kind of information as well, and things like that. So there's a lot of UX benefits to having this on chain, but in my view, it doesn't scale. So I'm not really sure what the long-term plan for memos is. I will say that from my perspective for Tachyon, we're just going to make it so that the shielded protocol doesn't care if the memos are on chain or not, and that's a separate concern that can be addressed in the future. We're going to decouple the actual cryptography that touches the proofs and the nullifiers and stuff from where all this other stuff that ends up on chain. So that in the future, if we want to get rid of that stuff because we come up with some interactive or XNet based payment protocol or whatever it is we do, we're not saddled with this extra stuff in our protocols. It's not coupled to the actual private payments that take place on chain, which don't actually need very much data. And certainly do not need to treat the blockchain as this data availability service effectively.
Yeah, it's really interesting, this long-term protocol evolution, because it does feel like a game of inches sometimes, where you're going to get a bunch of wins, not as many wins as you want. I think we've all experienced that one way or another, but this sounds like a great improvement. Obviously, even with memos, if they still stick around, it's a drastic reduction of on-chain storage still.
Yeah.
You're taking out the proofs, which are these giant blobs.
Talking about that specifically, so the way that the aggregation works that I was talking about a moment ago. So I post my transactions, they have proofs in them, they're large. In fact, they get larger in Tachyon. The Tachyon transactions are like twice as large, at least. So, or roughly, I don't know exactly. So you do that, but the transactions don't have to be included in the block with those proofs. They can be stripped out. And you can use recursive proofs, naturally, to combine them or aggregate them together. So the block producer, either themselves or with the assistance of some third party that wants to spend cycles doing it, can prove that the original recursive proofs that were in two or more transactions actually were valid, while also just having one recursive proof. So you still reveal your nullifiers. It's just that you end up, quote unquote, compressing all the proofs together in a block, so that, like I said, the marginal size is like a few hundred bytes or something like that for transactions once they enter the block. Before they enter the block, they still have these big proofs in them, like when they're being broadcast and relayed over the peer-to-peer network or whatever. But once they get into a block, they can be compressed down like that.
Yeah, they're generally ephemeral.
Yeah. And I think it's worth mentioning that the reason it makes sense to do the aggregation and this nullifier thing at the same time is because they both are two completely different ways to use recursive proofs. If you're using recursive proofs to do this, you might as well use recursive proofs like the aggregation. You might as well use them for the nullifier non-inclusion. You might as well use it for the whole entire protocol. So, in fact, you're not creating a traditional snark anymore on your phone with Tachyon. You're making a recursive proof because it all is using the same construction. So that's the reason why it's sort of all done at the same time in this one.
You create the recursive proof on your phone, and then you send that to these. We haven't actually said the term yet, but these oblivious syncing servers.
Right. So these proofs, like you are creating a recursive proof locally, but it isn't like you're using, like you're creating that recursive proof about certain parts of the statement that you actually care about or have the information to supply, like the witness information, locally. So you can prove, hey, I got some money, but maybe you don't prove that you can spend it. You let the service that you're talking about, this oblivious syncing service, make that proof that we can actually validly spend the money, give that to you, and you fold it together locally. So all the steps you have to prove locally, you kind of write them in terms of recursive proofs. Fine, it's just an extension of snarks. And then you fold them together so that all the pieces that you're trying to prove are kind of folded together. In a similar way, the block producers are folding together these proofs that they see in the original transactions in order to strip them out to compress them. So
it's like a truth sluice or something. Like it has this way of destroying data in all these different stages, but still preserving the truth of them.
It's certifying the state, but destroying the interstitial transitions.
Mm-hmm.
Yeah.
Very nice. How do the oblivious syncing servers, what is oblivious syncing? Why is it called that? And how do they preserve the privacy of their users?
So the idea behind oblivious sync is essentially just a formalism or a pseudo-formalism of the concept of doing what we're doing here, which is it's like the simplest way to think about what you're doing is you have a proof locally that you can spend money, and a remote server can assist in keeping that proof up to date as new transactions are created on chain, in order to make it so that when you reveal that proof, it's not only valid but also has the greatest anonymity set, and that service can do so without learning your wallet information and your node information. And in fact, we actually have an oblivious syncing service right now in Zcash, believe it or not.
Woo!
We already have one. Everyone's using it. If you're using shielded transactions, I'm being a little bit abusive of the terminology somewhat, but it is true that Light Wallet D, you're using Light Wallet D to help assist you in keeping your notes spendable. So a light wallet D server, while it may not work precisely the way that I envision a oblivious syncing service will work, you ask light wallet D for information that lets you sort of quote unquote update your spendability condition or predicate or whatever to match the current state of the chain. Every time your wallet does this, you open Zottle or whatever wallet you're using, it's downloading this information from Light Wallet D or Zano or whatever, and it's getting that information and using it to prove that you can spend your money. Now, in the existing protocol, you don't need to prove that you've not double spent before, right? Or that you spent before. In the new protocol, you do. And so that gives a new role to this remote service, this oblivious syncing service, where not only is it saying, okay, you did have money at this point in the chain has moved forward, you still have money, obviously, and here's the information you need in order to create the proof locally. Not only does it do that, but it also needs to prove that you haven't spent money in the meantime. And so it does those nullifier non-inclusion proofs, which, as I just explained, the service doesn't learn about your wallet in the process of doing that. So it doesn't learn about your notes. And so that's the sense in which the service is oblivious. It doesn't learn anything about your wallet. It doesn't learn anything useful.
You say, here's a bunch of valid stuff, and it says, okay, cool, I'm going to do computation on that and send you back something else that's also valid.
Indeed. And in this formalism, you can think of it in a very primitive sense as I half spend my money, but I don't actually know where I'm going to send it. But I create a proof that spends it, sort of, but up to a certain point in the history of the chain, and it's valid. And I could use it locally to spend if the chain didn't advance. But then I give that proof, or a re-randomized version of it, to the service, and the service, at my request, will advance the proof forward as the chain progresses, and as new nullifiers appear on chain that you have to prove non-inclusion of. And then it hands it back to you, and you can re-randomize it again and attach it to your transaction and spend it. So that's the way in which to think of oblivious sync in a real a formal sense. However, proof carrying data is very, very flexible, so the actual architecture doesn't necessarily have to work like that. You don't necessarily have to give the service an incremental proof that it only advances one block at a time. You could potentially have, like we were talking about a moment ago, you could have many servers in parallel constructing non-inclusion proofs for different epochs on chain, and those get stitched together. Either they could stitch it or you could stitch it. So there's a lot of flexibility, but in the very primitive sense, the oblivious syncing service is like a state machine, or is advancing a state machine for us. But they don't have to learn about all of the state. They only learn about the state that they touch. So they can go, okay, now at block height blah, this is valid, and to make a new proof that advances that counter and that's the part of the state, all the other state comes with it, but that counter gets incremented, and all they have to do is make sure that they satisfy the predicate, the non-inclusion proof, or whatever it is that they're doing. And so that's the sense in which oblivious syncing services work in that model.
Cool. Okay, thank you, Sean. We are at the hour here. I'm willing to keep going, and I'm sure people have questions, so I'll propose that, Sean, we go until we run out of questions, or you say, I'm done.
Sounds good to me.
All right, so Squirrel asks, is LightWallet D / Zyno still needed? Do we still need indexers, basically? What does the wallet submit the transaction to?
Yeah, it's a good. So the reason why we have indexers now, there's multiple reasons, but the main reason is to actually discover when we received a payment, right? So when we close our wallet, and reopen it later, we need to figure out if in that intervening time we received a payment, because we could have. And so what you do is you actually ask these servers to give you every transaction that's ever happened on chain, and you scan them locally to figure out which ones are for you. And the service doesn't learn necessarily, doesn't learn which notes that are actually for you, or which transactions were for you necessarily, but you do have to download all of them. You have to download all of the transactions in order to do this scanning process, which is really annoying and doesn't scale. So you'll notice that part of the problem is separate from everything I've discussed so far. Because nothing about the nullifiers has anything to do with learning where you received your money. Nothing about the aggregation protocol has anything to do about learning where your transactions are on chain. And none of that has to do with backup and restore either. So all of that is part of the payment protocol. The payment protocol is, how do I communicate to my recipient that they have money and it's spendable, it's on chain, and give them the information they need to spend it? How do I affect the payment? And the payment protocol is responsible for this in today's protocol in Zcash. That's integrated directly into it's very coupled with the existing shielded protocol. On chain, you have these ciphertexts that contain all the information you need, and every user downloads every ciphertext and trial decrypts it and tries to receive the money that way. In the future, we can't do that. It doesn't scale. So, what do we do instead? Well, Tachyon doesn't solve that problem, but it does highly, by this decoupling process, highly encourage the payment protocol to solve it. And the payment protocol can solve it. There's different ways. There's a group that's working on, I don't want to name drop them or anything yet, because I don't know if they're going public yet, but whatever, whenever that happens. They are building a payment protocol prototype for Tachyon, which would allow using this really clever cryptography called private information retrieval, which would allow your phone to effectively ask a service to scan the blockchain for you and then give you back an answer that says, here's your money, except the service doesn't actually learn actually where your money is or anything about it. It doesn't learn anything. And it uses some really awesome cryptography that's only recently become semi-practical enough to do this at scale. So if that's the case, and we use that in our payment protocol for Tachyon in the future, then you get a lot of the same UX design kind of trade-offs. Everything kind of works a little bit the same as how you have transactions today, except you aren't scanning the blockchain, you're having some service do it for you. You'll notice this theme of having a service do something for you, but then not invade your privacy is very central to everything we're doing. That's essentially our scaling roadmap, is to lean heavily on changing the protocol in any way possible to make it so that remote services can do all the work, but the local user retains all their private information.
Is that some sort of homomorphic encryption?
It does. It uses lattice-based cryptography. It uses homomorphic. Technically, homomorphic encryption can be used to build PIR. I think it implies PIR, but they're separate primitives. But yes, I think the construction they're using does use the same exact assumptions that you would use in fully homomorphic encryption. Lattice-based assumptions.
Cool. What is an epoch in your terminology?
An epoch is just a set of blocks, let's say 100 blocks, just for the sake of argument, is an epoch. So after an epoch, your nullifier changes. So now when you want to spend your money, you have to reveal a different nullifier.
Okay.
Yeah. And you have to reveal publicly a different nullifier, but you have to prove non-inclusion of that old one still. And all the ones that took place before that for your note.
Oh, that's interesting. So if I have a note that I hold for a week, I have all those epochs kind of on my phone hanging out, or I have to prove all those.
When you say epochs, what do you mean?
Well, 100 blocks for the sake of argument.
So let's say the local phone has the blocks, is what you're saying?
Well, I'm just trying to dig into what you said about I have to prove the inclusion of all of my nullifiers.
I'm being a little bit so the service does it for us, right? We can trust the service to do it for us because the service doesn't learn about the nullifier we actually reveal on chain, and so that's the trick. But when I say we have to create a proof, I'm overloading things a little bit. It's the service that's doing it on our behalf. We just don't have to worry about them like invading our privacy in the process. Yet, like morally speaking, we are responsible as users for procuring that proof or creating it or whatever, and attaching it or integrating it and folding it into the proof that we post in our transaction. Yes, the idea though, you don't necessarily, and this kind of gets at maybe what you're saying, you don't necessarily need the services, right? You can create the proofs locally if you want. If you're willing to download all the blocks, you can do the same thing the services are doing. You actually have all the cryptography sitting there, and you can do it yourself.
Do you see the full nodes evolving to these oblivious syncing servers or having these oblivious syncing capabilities? Like, will people just run Zebra the way they normally do, and it would just do all this stuff?
I'm not sure that the full nodes should be doing, like, you don't. This goes back to some questions you're probably getting in the chat now, which is who's going to pay for these services, how expensive are they, and stuff like that, which are very good questions. The full nodes are already doing like a heroic service for the network, essentially giving up storage and especially bandwidth to the network in order to make it so that everyone can download the whole history and stuff, right? And they're also partly helping in ensuring that everyone checks the consensus rules or giving them some reason to do so. It's also important, otherwise there's no point in all this. So yes, the full nodes are important for that role. If you added another role to the full nodes, it would be very complicated incentive-wise. These services need to be different from full nodes, in my view. They can't. I mean, you first off, you need to somehow finance them in a way that full nodes can operate altruistically in our network. Maybe, like barely, arguably, but I doubt that these oblivious syncing services can. The amount of computation at scale that they'll have to do is just too high.
Freaknik asks in the chat, lattice-based cryptography is quantum resistant, if I'm not mistaken.
That's right. That's right.
Also, we didn't touch upon this, but Tachyon, if you remove all the stuff from the chain, is quantum resistant because you can't decrypt something that doesn't exist.
It's quantum private.
Quantum private, sorry. It's like Eddie Murphy tapping his forehead. Like, you can't, there's nothing there. So, yeah.
Yep.
Is lattice-based cryptography quantum resistant?
Yes. Well, I mean, it depends on the assumptions, but yes, the ones that people generally think of using, as far as we understand it, are indeed quantum resistant. Obviously, like, that doesn't mean that every protocol that uses quantum-based assumptions is going to be quantum resistant, right? It really depends on how your construction works, but a lot of these new protocols are indeed quantum resistant. There are some protocols I can't think on the top of my head, but at least I could conjecture protocols that would be designed to use lattice-based assumptions purely for optimization purposes, or because really the only practical way that we know how to do fully homomorphic encryption or PIR and things like that use lattice-based assumptions. You might not actually care about quantum resistance. You might just want to use lattice-based assumptions simply to create those primitives. So you might not even parameterize your construction such that it's quantum resistant, simply to get some performance out of it. I don't know exactly what the trade-offs there are. I'm not a huge expert in quantum resistant crypto. That's a good question for some of the other folks that are working on cool stuff like that right now in Zcash.
Cool. Tim says, I have a thing to layer on top of Lattice I'm working on that fixes my personal issues with it. Sort of a new KEM. Okay. Cool.
Cool.
I don't see any other questions right now.
Okay.
Wrap up here. Do you have anything to plug? Actually, we haven't looked at the website. people, I'll place it in the chat here.
What website? What are you talking about? I don't know what you're talking about. Just kidding.
Oh, okay. Somebody made a fan site.
No.
Oh. I know. Okay. Can I paste it?
Yeah, no, that's fine. It's okay. We just have a little placeholder website, which is going to have some interesting stuff on it soon. So, but there's a little placeholder website that we have for the project.
Yeah, people should
Stay tuned.
It's got a good roadmap, and yeah. Well, good luck to you and your team, Sean. I think you're doing good work, and keep it up.
Thank you very much. This was really cathartic to do a horrible job explaining my project to everybody.
There's a good audience for it too. There's a lot of technical people in here. So,
yeah.
Thank you, everybody, and thank you again, Sean.
Thank you.